Welcome to our physics problem set covering the topics of torque and angular acceleration. This first problem says a uniform ladder of mass m and length L rests against a smooth wall at an angle theta as shown in the figure. What is the torque due to the weight of the ladder about its base? All right, so this part right here where it says about its base is telling us that our axis of rotation is going to be at the base where the ladder is touching the ground. And that's kind of easy to visualize because if we were to kind of make this wall disappear, then what would happen to the ladder? It would just fall straight downward, and the axis of rotation would be about the base where it's touching the floor. That said, the question is, what is the torque that's being generated due to gravity? So one big assumption that we have to make here, and this kind of just comes with, understanding of the topic, is that gravity acts at the center of mass of an object. And generally, when you have a lever arm that's kind of uniform throughout, it's kind of the same shape all the way through. It's like a bar or a ladder. We're going to assume that it's uniform. That means that its center of mass is going to exist at its center point, all right? So then when we have to decide where specifically gravity is acting on an object, we always say that it's acting specifically on its center of mass. So we're going to point at this center point on the ladder, and we're going to say that there's some force due to gravity, and let's zoom in here a little bit. We're going to say that there's some force due to gravity downward. And that force due to gravity downward is going to be equal to mg, where m is the mass of the ladder and g is the acceleration due to gravity. All right. One thing that we need to know about this topic is that only forces that are perpendicular to our lever arm actually generate torque. Our lever arm is the ladder. So only the component of gravity that is perpendicular to the ladder is going to actually generate any torque. So what I'm going to do is I'm going to draw a right triangle that breaks up this force vector into two perpendicular components. One component is going to be perpendicular to the lever arm, and one component is going to be parallel to the lever arm, so that those two components together will make up this force vector, and this is how it's done. All right. So I'm going to do my best to draw a line that's perpendicular to the lever arm, and then a line that's parallel to the lever arm. And that should come together as a right triangle, with the hypotenuse being the actual force vector due to gravity. All right. Now, here's the tricky part as far as the trigonometry is concerned. We are given that this angle is equal to angle theta. All right. So that means that this angle, and I'm going to do it in red, this angle right here is also equal to angle theta, and it's not always easy to visualize that immediately. So let's chat about it, all right? Because our force vector due to gravity makes a 90-degree angle with the floor, all right? So we know that we have a triangle right here. So eyes on the screen. We have a triangle right here that has a 90-degree angle here, some angle theta here, and then there's a third angle here that is complementary to this angle theta. That means this angle plus angle theta equals 90 degrees. So we have a similar situation with our perpendicular component of gravity to the lever arm, making a 90-degree angle with the lever arm. So that means that our angle inside the triangle we just drew, along with the third angle from the original triangle, also must be complementary. That's how we can make a statement that this angle in red here is equal to our angle theta. All right, so now that we've established that this is indeed angle theta, all we need to know to figure out how much force is working to generate torque is we need to take the magnitude of our force due to gravity and multiply it by, and I'll do this in green, take the magnitude of our force due to gravity and multiply it by cosine theta, because cosine theta always gives us the magnitude of the leg that is adjacent to the angle that we know. Good, so this is the force due to gravity that is generating torque on our lever arm, on our ladder. So then what we have to do from there is we have to go ahead and recall that torque generated, the equation for torque generated, okay, is equal to distance from the axis of rotation times the force that is perpendicular to your lever arm. All right. Sometimes you might recall this being the equation RF sine theta, but that sine theta is just there so that you can use sine theta if you know what angle that your force makes directly with the lever arm to find the component that's perpendicular. But in this case, we're not actually using the angle that is directly made with the lever arm. We're using a different angle based off of the trigonometry you see here. So that's why it's ending up being cosine theta. But this whole thing right here, mg cosine theta, represents the force that is perpendicular. So that means we can go ahead and drop our trigonometry. So that's why we're just using RF, because we know that our F is already perpendicular, because we went ahead and on our own, we found that perpendicular component. That said, the torque that's generated must then be equal to the distance from our axis of rotation. We know that the full length of the lever arm is L, but we know we're also working at the midway point, so we're going to say L over 2. L over 2 is where force of gravity is acting on our bar from the axis of rotation. And then we're just going to multiply that by the force that we just found here, mg cosine theta. Now this expression here should represent the amount of torque that's generated by gravity. So there should be an answer choice that looks something like this. Right here. You could put the whole thing over 2 instead of just L over 2, and you'll have the exact same thing that we have here, mgl cosine theta over 2. The answer choice is D. In this problem, we have a figure that represents a top-down view of a lever arm, with the black circle being the axis of rotation. There are 4 different points in which forces are acting on our lever arm, and they're all equidistant from each other. All right, so let's read the question. The figure above represents a stick of uniform density that is attached to a pivot at the right end and has equally spaced marks along its length. Any one or a combination of the 4 forces shown can be exerted on the stick as indicated. Now, right now, I'm going to highlight the fact that any one or a combination of the 4 forces can be exerted on the stick as indicated. The question is, 2 of the 4 forces are exerted on the stick. Which of the following predictions is correct about the change in angular velocity of the stick per unit time? All right, so unfortunately, this is just one of those problems where we might just have to read through each answer choice and consider each one. A says, when F1 and F2 are exerted on the stick will have the greatest change in angular velocity per unit of time. All right, so it's saying that basically, A is saying that these 2 forces are going to generate more torque than these 2 forces. That's generally what it's saying, and that choosing only these 2 forces and leaving these out will represent the greatest amount of magnitude in net torque on the bar than any other combination of choices. And that kind of makes sense because these 2 would work against these 2. But the question is, will these 2 forces generate more torque downward than these 2 forces would generate upward? And you might be like, okay, well, yeah, they're 100 and 200. The other ones are 25 and 50. Well, I wouldn't be so quick. I would suggest that, yeah, that's true. But remember, being further away from the axis of rotation also increases the amount of torque you're going to generate. So let's write down the formula for torque really quick, just so we know. Torque is generated by the distance you are from the axis of rotation times the force that's perpendicular to the lever arm. All of our forces are perpendicular to the lever arm, so we don't have to worry about any trigonometry here. But once you see this, you'll see that both of these are directly proportional to torque. So that means that if you half one, you have to double the other one in order to maintain the same torque. All right. So basically, the fact that 200 newtons of force is 8 times 25 newtons of force. However, it's not 8 times closer, means that this will generate more torque than this. Right? And then the 100 newtons of force, it's twice as much as the 50 newtons of force, but it's not half as close. It's actually 33% closer, or yeah, something like that. All right. It's not half as close. Half as close would be like somewhere over here. That said, the F2 is going to generate more torque than F3. So both F1 and F2 combined definitely generate more torque than F3 and F4 combined. Hopefully I didn't confuse you there. The point is that, yes, A is true. F1 and F2 do represent the choice of forces that would generate the most torque on the lever arm, which would in turn have the greatest change of angular velocity per unit of time, all right, because it's going to have the greatest angular acceleration. the amount of torque you have is directly proportional to how much angular acceleration you have. That said, I'm going to go ahead and circle A, but let's take a look at the other choices first. When F1 and F3 are exerted on the stick will not change its angular velocity per unit time. So it's saying that F1 and F3 together will cancel each other out. F1 and F3 together, will they cancel each other out? Well, F3 is 1.5 meters away, F1 is 0.5 meters away, so that means the torque due to F1 should be 100 Newton meters, and then the torque due from F3 would be 50 times 1.5. That's about, 75 Newton meters? So they will not be in equilibrium. So B is not true. For C, it says F2 and F3 are exerted on the stick. The stick's change in angular velocity per unit time will be in the clockwise direction. So if we take F2 and F3, then it will be clockwise. Well, we already discussed that F2 generates a greater torque than F3. So no, already it would be counterclockwise if we chose these two. So it would not turn this way. It would instead, in purple, turn this way. All right. So C is not correct. Now let's look at D. When F3 and F4 are exerted on the stick will have the smallest change in angular velocity per unit of time. F3 and F4. Okay, so this is actually the tricky answer choice, because you might be like, okay, F1 and F2 represent the largest torque generated. F3 and F4 must represent the smallest torque generated. And I would imagine that a lot of students might actually be like, well, aren't they both true? But the problem is, and I'll go back and I'll say, we highlighted that choosing only one is an option. So choosing F3 or F4 alone would both generate smaller torque than choosing them both together. So that's why D is not correct, because we don't have to choose two forces. We could just choose one force, and that one force, whether it be F3 or F4, would result in a smaller change in angular velocity per unit of time. All right, so that's why D is not correct. Here we have two different experiments with their data plotted on an angular momentum versus time graph. All right, so we have experiment 1 and experiment 2. All right, let's read the question. A horizontal disk is at rest on top of an axle, and the friction between the disk and the axle is not negligible. In experiment 1, an applied torque is exerted to the edge of the disk for 2 seconds. All right, so we can see, so let me highlight that, what I just read. In experiment 1, an applied torque is exerted to the edge of the disk for 2 seconds. And if we look at experiment 1, we can see that at the 2-second mark, there's kind of a quick change in the angular momentum. So for the 2 seconds leading up to that 2-second mark, we notice that the angular momentum was increasing at a constant rate, okay? But then once that net torque stops, because friction is not negligible, the angular momentum is going to decrease back down basically into the point where it stops, where it has no more angular momentum, all right? So at the moment that the applied torque is removed at that 2-second mark, and the disk eventually comes to a rest as a result of a friction torque, let me see, yeah, so that's what happens in that first 2 seconds, and then it comes to a stop due to torque by friction during this period. So from the 2-second period to about the 5.5-second period. Graphs of the disk's angular momentum as a function of time are shown in figures 1 and 2. Which of the following statements is correct about the applied torque and the friction torque? Okay, so before I even look at the answer choices, let's actually just investigate what's going on here. Because it looks like in figure 2, we also only apply the net torque to the disk for 2 seconds. Because I'm seeing the exact same change at the 2-second mark here. The main difference is that in experiment 2, we reached a much higher angular momentum during that 2-second period. All right. And then from that point, the friction worked on the disc until it came to a stop. Now, naturally, it took longer to come to a stop because it reached a higher angular momentum. But here's the physical principle that I need to remind you of here that we're actually truly dealing with. We have to remember that torque, just like Newton's second law in terms of momentum, torque also has a relationship with angular momentum. Torque can be represented as the change in angular momentum. Remember, capital L represents angular momentum over the change in time. Now, what's special about that is that these graphs are angular momentum over time. So if we take the change in our y over the change in our x, that represents the slope of the graph, right? That's the definition of slope on a graph, change in y over change in x. So we can find out how much torque that the disk is experiencing at any point on these two graphs if we just take the slope, all right? So if we look at the first experiment, we have a certain slope that represents 20 over 2. So that's 10. That's a slope of 10, all right? So our torque is 10 Newton meters. That said, if we look at it, so we have a torque of 10 Newton meters in our first 2 seconds. Torque is equal to 10 Newton meters. And I haven't even read the answer choices, by the way, yet. So we're just investigating the graphs to make sure that we understand what's going on here. Over here for experiment 2, we have 40. We reach 40 in 2 seconds. So that's 20 Newton meters of torque. Very nice. So clearly in experiment 2, we're generating more applied torque, right? But then if we look, and I don't even really have to do any math here. If I look here, okay, at the downward portion of this slope, and I take these, oops, we don't want to do that. All right. I take these, I look at this downward portion of the slope, and I recognize that they're basically parallel to each other. Then I can pretty much assume that they have the same amount of torque. And, you know, we could go ahead and say like 40 over, how long did this take? 8 seconds. Like 40 over 8, that gives you 5. All right, we can kind of do the same thing here. Let's say that it went all the way to 6 here. 20 over 3, or let me see, 3, 4, 5, 6. Yeah, 20 over 4. That gives you 5. Yeah, so they looked parallel already, but now that we see that they have the same slope, we know that the friction is actually applying the same frictional torque on both of them. So, all right, so here's what we know now. We know that for the 2 seconds in experiment 2, there was more torque was being generated, but for both experiments, the friction which caused it to come to a stop was the same. All right, so let's look at what our answer choices are. Okay, so it is asking about applied torque versus frictional torque. Answer choice A says that experiment 1 had more applied torque. We know that that's wrong. Answer choice B says experiment 2 had more applied torque. That's true, but it also says that there's a difference between the frictions, and we know that that's wrong. All right. Answer choice C says that experiment 1 had more applied torque because that's the greater than symbols. So yeah, don't forget your greater than and your less than symbols. All right. That said, we know that experiment 2 had more applied torque, so C is wrong. And by process of elimination, we know the answer choice is D, but let's just look at what it says. It says experiment 2 had more applied torque. It says experiment 2 had more applied torque. And then it says that their frictions are equal. All right, yeah, that's exactly what we said. The answer choice is the correct answer here is D. All right, here it looks like we have a uniform horizontal beam. The beam looks like it exists right here. All right. It has mass capital M, and length L. And it's attached to a hinge at point P. So it's actually attached here, and we're going to consider that the axis of rotation. So if we were to cut this string, then it would probably just fall down this way, staying attached here at point P. All right. The opposite end of the bar, however, or the beam, is supported by a cable. So here's the cable. The angle between the beam and the cable is angle theta. All right, good. So we have that. What is the magnitude of the torque that the cable exerts on the beam? All right, so we want to know how much torque is generated by this cable. Now, here's the thing is that we're going to have to assume here that this bar is currently in static equilibrium, meaning that it's not currently rotating. So this cable and the torque generated by it, or at least the torque generated by the vertical component of the force and tension in this cable, has to be balanced out by the torque that's generated by the force due to gravity on the bar. All right. So that's an important thing to understand, because I'm looking at these answer choices, and all these answer choices are in terms of mg. So that means that the expression for the torque generated by the tension in the cable is equal to the expression for the torque generated due to gravity. And I'd prefer to figure out the expression for the torque generated due to gravity, because guess what? The force of gravity is already perpendicular to this bar. And if I work on finding that expression, I don't have to deal with as much trigonometry, because when we already know that the force applied is perpendicular, we can drop any trig functions on our torque expression. That said, let's figure out what the torque is that is generated by gravity. So we know that the center of mass of this uniform bar is going to be somewhere in the middle. And we also know that the magnitude of the force due to gravity must be capital mg, capital M being the mass of the bar and g being the acceleration due to gravity. Now, gravity is already working perpendicular to our lever arm, so all we have to do is multiply that by the distance from the axis of rotation, which the axis of rotation is p, so the distance from that axis of rotation right now is L over 2, because it's half the distance from the edge of the bar. So then I can say that the torque being generated by gravity is just equal to L over 2 capital mg. And that should be equal to the torque that's generated by tension in the cable. And it's asking, what is the magnitude of the torque that's generated by the tension in the cable? Well, it's just this. Is there an answer choice that looks like that? Yeah, absolutely. A. Hope you like that one. So here it looks like we have a figure of a cannon that has some initial velocity moving to the right, and then the same cannon at some time later that has some final velocity still moving to the right after having launched a projectile. The question says, a cart with a toy projectile launcher attached to its top travels forward at a constant speed v0. Okay, that's the initial point, the initial velocity. The launcher fires a solid sphere forward at a speed much greater than that of the cart launcher system. The cart's speed after firing the dot is v final is less than v initial, and that sort of makes sense because equal and opposite reactions. When it launches this ball, there's going to be a force in the opposite direction on the launcher, so that should cause some deceleration to occur. So our final velocity should definitely be smaller than our initial velocity. All right, so the cart's speed after the firing dot is less. Frictional forces are considered to be negligible, so that's nice. Which of the following scenarios best represents the rotational analog to this situation? Okay, I can see that last sentence actually being kind of confusing to a lot of students. This question is really just asking you to, and let me highlight what I'm talking about here. Which of the following scenarios best represents the rotational analog to this situation? All right, so clearly this is a linear problem. This is a linear translational problem, and it means an object is moving in a straight line and the object that it interacts with is also moving in a straight line, okay? There's nothing rotational or angular about it. That said, it's asking you to consider the problem, which has to do with an object launching a projectile and slowing itself down. That's exactly what just happens here. And see which one of the answer choices represents a rotational motion version of this problem. Analog is just analogous, like an analogy. So we're looking for a rotational analogy to this linear problem, right? So a little bit of vocab here in the physics test, all right? A says a gaseous planet rotates with a large rotational velocity, causing the middle of the planet's equator to bulge outward. First off, answer choice A doesn't have a projectile, and it doesn't have anything to do with the velocity of the rotation slowing down. All right, so I'm going to skip A. So A is not correct. B says a spinning platform falls onto a stationary platform. Both platforms rotate together, but at a smaller common rotational speed than that of the spinning platform immediately before the collision. All right, this one's a little bit closer because at least it has that component to where we had some initial velocity and then a slower final velocity. But I don't like it so much because it doesn't have a projectile. So I'm going to say hold off on this one. Let's see if there's a better analogy to our linear problem up above. C says, a child on the edge of a large rotating disc throws a ball in the same direction of its original rotation. Okay, cool. So this one does have a projectile. All right. The thing is that it doesn't really mention the fact that the velocity is going to get slower, but you can assume that the velocity is going to get slower because some force had to be pushed backwards when the child threw the ball. So we know that the angular velocity is going to slow down if we throw a ball in the same tangential direction as the tangential velocity of the child. So actually, I do like C. I like C, and in fact, I like it better than B right now, just because there is a projectile. All right, and then D says a figure skater spins the skater's hands at the skater's waist. When the skater extends the arms outward, the skater's rotational velocity decreases. Interesting. So this problem does also show the decrease in velocity, but there's no projectile. It's suggesting, and the thing about it is that the figure skater is going to slow down, but not because of a force that's acting on the figure skater's arms, more like because of the fact of conservation of angular momentum is why the figure skater in D is going to slow down, because they are changing their moment of inertia, so their velocity has to change so that momentum can stay the same. So D is not actually it. It's kind of playing with a different physics principle. C is going to be my answer choice here because a child on the edge of a large rotating disc throws a projectile in the same tangential direction of the child's tangential velocity at that point. We know that there's going to be an equal and opposite force back on the child, which will result in the velocity of the spinning disc slowing down. So we're going to go with C because that's basically the same thing as what's going on in our linear problem up here, just in a rotational sense. Here we have a uniform cylinder of radius r, mass capital M, and rotational inertia I. That's good that we know the rotational inertia. And this uniform cylinder is initially at rest. The cylinder is mounted so that it is free to rotate with negligible friction about an axle that is oriented through the center of the cylinder and perpendicular to the page. All right, so we can see all that here. We have the cylinder, I can start coloring in the cylinder here. There's an axis that goes straight through it. All right, and it looks like there's going to be a force tangent to the edge. And one thing that I want to make a statement here about this force is that if this force is indeed tangent to this circle, then that's the same thing as a force being perpendicular to the lever arm. So when an entire cylinder, when an entire disc is spinning, all right, then anything that's tangent to that disc represents being perpendicular to the lever arm, like we were discussing lever arms in previous questions. So that means that whatever force this is, we can just multiply that by the radius from the axis of rotation, and that will give us our torque. We can drop any trig here, so that's really nice. All right, let's see. Where did we leave off? A light string is wrapped around the cylinder. At time t is equal to 0, the string is pulled with a constant force F0, which causes the cylinder to rotate. As shown in the figure, after time t, the string is completely unwound from the cylinder and loses contact with it. If necessary, how can a student determine the change in angular momentum delta L of the cylinder from time 0 to time t? Great. All right. That said, we are looking for delta L, which in other words is called the impulse. So that immediately should bring to mind the impulse-torque relation. All right. So the impulse-torque relation is this. Delta T, and it is derived from Newton's second law, by the way. So if you just know Newton's second law in terms of torque and angular momentum, then you can get this very easily. Delta L, which we call our impulse, is equal to torque times delta T, so our change in time. That's great. So we don't know torque yet, but we do know how to find torque because we have our perpendicular force and we have our distance from the axis of rotation. So I'm just going to rewrite this a little bit, and I'm going to say that delta L, our impulse, must then be equal to F0 times our distance from our axis of rotation times delta T. And we know delta T, we know R, and we know the force that's applied. So if we're looking for delta L, the impulse, how can the student determine the change in angular momentum? All we need to do is we need to find these three values and multiply them together. There should be an answer choice that looks just like it. Let's read through them. A says, a determination is not necessary. The cylinder does not have a change in angular momentum. That's false. If there's a force applied tangent to the cylinder and it's free to rotate, then it will definitely have a change in angular momentum. B says multiply F naught R and T to calculate. That's exactly right. The quantity is equal to delta. That's exactly right. All right. All right, so here we have a figure where it looks like we have a meter stick attached to a string and it's being balanced due to the torque generated being in equilibrium on both sides of the meter stick. All right, so one end of a string is attached to the ceiling and the other end of the string is attached to a cradle that has a meter stick that runs through it. The meter stick can slide through the cradle so that the horizontal position of a point on the meter stick can be changed. All right, fine. Students may hang objects of various masses from the meter stick as shown in the figure. The students notice that when the meter stick cradle object system is not balanced, the meter stick will rotate. Yeah, that makes sense because it's not in rotational equilibrium if we don't have the same amount of torque being generated on both sides of the cradle. All right, so it looks like this version of the figure is in equilibrium, so we can assume that these two objects are the same mass. That's great. Let's actually zoom in and see what's going on down here. It says, consider the situation shown above in which the center of the meter stick is aligned with the center of the cradle. Okay, great. Which is at position x is equal to 0. Okay, we'll say that that's position x is equal to 0. The system is released from rest. Which of the following claims is correct about the motion of the system containing the meter stick, cradle, and two objects if the system is free to rotate? All right, hold on. Before we even look at the answer choices, and this is how I always do it, I kind of just try to investigate what's going on here in the figure. All right, so I do know that since these two masses are the same, and gravity is working on both of them with the same amount of acceleration due to gravity, then we're going to have a net torque downward on this side of the meter stick, just because the torque generated by gravity on this guy is just going to be mg times 0.25. And I should have just written that in pen. Mg times 0.25, because it's distance from the axis of rotation times the force that's perpendicular to your lever arm. So that's exactly what we have here. So that's downward. And then on this side, we have the same mg, but this time it's times 0.5, which is a larger number. So we're going to have more torque being generated by this mass because it's just farther away from the axis of rotation. So what's going to happen is, like, as soon as this is left to fall in whatever way it may, this meter stick is going to tilt downward and it's going to tilt downward due to a net torque that is downward. And when I say downward, I really mean clockwise, because if it was going to go this way, if it was going to fall on the left side, then that would be counterclockwise. But what's going to happen is that it's going to fall on the right side, which is going to represent a clockwise motion. You can probably imagine. That said, because it's going to fall in the clockwise direction due to a net torque, that means it's going to have some net angular acceleration. And net angular acceleration means that its velocity is going to be increasing for some time. Now, we're not talking about some long time after, but immediately when we let go, its angular velocity is going to be increasing in the clockwise direction. All right, so now that's basically everything we can say right off the bat about this figure. Let's see what the answer choices say. A says that the system will rotate in a clockwise direction with constant angular speed. Ooh, tricky. It's true that it will rotate in a clockwise direction, but not with constant angular speed. Because there's a net torque, there will be, just like I just said, angular acceleration. So the angular speed or the angular velocity will not be constant. All right, so A's out. B says that the system will rotate in a clockwise direction with increasing angular speed. That's exactly what's going to happen, all right? So B's the correct answer. Let's move on. All right, here we have a new problem, but with the same setup, at least the same premise for the figure, all right? So we don't need to read this portion again. It's the same as the previous question. That said, let's go ahead and zoom in here with what we're really dealing with this problem. All right, it says, consider the situation shown above in which the center of the meter stick is aligned with the center of the cradle, which is at position x is equal to 0. So that's the same as the last problem as well. But then the last sentence says, which of the following statements is correct about the torque exerted on the meter stick? All right, so it's a very similar question to the last problem we just had, but there's one very important difference in that the masses are no longer the same. All right, in the previous question, if you go back, you'll see that they were both 1 kilogram, and we made a lot of statements about what would happen if they were both 1 kilogram. That said, this time they're not both 1 kilogram. One of them is half the mass of the other. We have a 0.5 kilogram mass here and a 1 kilogram mass here. So now we have to consider the relationship of how torque is generated based off of distance from our axis of rotation and the mass of the object. Great. So really quickly, let's go ahead and just remind ourselves what the relationship is that generates torque. Okay, so torque is going to be equal to your force that is, well, we should start with R. R represents your distance from the axis of rotation, which I currently have an arrow pointing to here, all right, times the force that is perpendicular to your lever arm. Of course, here the meter stick is our lever arm. And the force that's working on our meter stick is the string, the tension in the string, which is all generated by the force due to gravity. And in this setup, that's already perpendicular to our meter stick, so we don't have to deal with any tricky trigonometry. Great. So now let's create an expression specifically for this situation because we know that our force is going to be generated due to gravity. Instead of just saying perpendicular F, I'm going to say mg. All right. So for this side, I'm going to call it torque left, and for this side, I'm going to call it torque right. All right. So now for torque left, that's going to be 0.25, because that's how many meters we are from the axis of rotation, times mg, all right? mg, all right? And instead of mg, let's just go ahead and write it. If g is the acceleration due to gravity, which we're going to say is 10, and m is 1, we can just say 10 here, all right? So that's 1 times 10, all right? So then torque generated on the left side of our meter stick is equal to just 2.5 Newton meters. That's great. So we're going to have a torque generated in the counterclockwise direction, all right? Counterclockwise direction equal to 2.5 Newton meters. Great, so let's go ahead and figure out how much torque is generated on the right side. All right, it's going to be 0.5 times, now we take this 0.5 and multiply it by 10, mg, all right? Because that's what we're calling this force. We're calling this force mg. All right, we multiply that 0.5 by 10, and then we get 5. We get 5 newtons. All right, so that means that the torque generated by the right side is going to be 0.5 times 5, which is 2.5 Newton meters. All right, great. So what we've learned is that the torque generated on both sides here is 2.5 Newton meters. And if the torque generated on the right side is in the clockwise direction, while the torque generated on the left side is in the counterclockwise direction, then that means that they're going to be essentially canceling each other out. And if there's no other net torque, if there's no other torques acting on this system, then we can say that it is currently in equilibrium. All right. So then there should be no movement because the two torques are going to cancel each other out. All right, that's everything we can say about this. Let's go to the answer choices. A says the torque exerted by the force due to gravity is the greatest torque exerted on the meter stick. Interesting answer choice. The torque exerted by the force due to gravity is the greatest torque exerted on the meter stick. I mean, I guess that's true. That's a weird statement. Oh, okay, my mistake here. The torque exerted by the force due to gravity is the greatest torque exerted on the meter stick. This is saying that the torque generated by force due to gravity on the meter stick is the greatest torque generated. But that's not true at all, because the force due to gravity on the meter stick is being exerted at its center point. And that center point is 0 meters from the axis of rotation. So that's why the force due to gravity on the meter stick itself, due to the mass of the meter stick, doesn't generate any torque. So that's why A is definitely not the correct answer. If we go to B, it says the torque exerted by the 1 kilogram object is the greatest torque exerted on the meter stick. That's not true because it's equal to the torque exerted by the other object, so the B is not correct. C says the torque exerted by the 0.5 kilogram is the greatest. That's not true because we just said they're equal. D says the torque exerted by the 1 kilogram object is equal to the torque exerted by the 0.5 kilogram object. Yeah, that's what we did all that math to figure out. Let's go ahead and hit D and move on. All right, so in this problem, we have an experiment that a student is doing. So it says, in an experiment, a solid uniform cylinder of unknown radius r and unknown rotational inertia about a central axis is initially at rest. A light string is wrapped around the cylinder, as shown in the figure. The string is pulled with a constant unknown force, F naught, causing the cylinder to rotate. After an unknown time interval, delta T naught, the string is completely unwound from the pulley and loses contact with it. All right, to collect data, a student has access to a meter stick. Let's actually highlight this. This is important to know. A meter stick, a stopwatch, and a force probe. All right. The cylinder may rotate but cannot be moved off of its axle. Indicate whether the force applied to the cylinder F naught and the rotational inertia. Okay, so we're looking for the force applied to the cylinder and the rotational inertia. Can they be measured directly or calculated from measured quantities in the experiment? Okay, great. All right, so first off, a force probe generally is very useful in measuring tension in a string if you're able to apply it to one side of the string. So that's exactly what's going on here. All right. So we can very easily apply the force probe to the other end of the string as you're pulling it off the cylinder to figure out exactly what F naught is. So that means that F naught is able to be measured directly. No ifs, ands, or buts about it. So I'm going to look at my answer choices here, and I see that A and B suggest that F naught can be measured directly, and those are the only two, so I'm going to cancel out C and D right off the bat there. All right, now between A and B, the difference is that it's saying that the moment of inertia can be measured directly, or it can't. It can be calculated from measured quantities. And with my expertise, I say I am automatically going to go with B because I know that I don't have a way of measuring the density of the cylinder, so it'd actually be really difficult for me to measure the moment of inertia. I mean, you can look at the cylinder and see that it's a cylinder, and you can find an expression for calculating moment of inertia based off of mass, but that's not the same thing as measuring it directly, right? Measuring moment of inertia directly is very difficult. That said, we could figure it out though using Newton's second law in terms of torque and angular momentum or angular acceleration and moment of inertia. So that means that torque is equal to moment of inertia times angular acceleration. All right, so we can very easily find torque because we know we can measure force directly. All right, but then for finding angular acceleration, we'd have to make sure that we're applying a constant force and actually use one of the kinematic equations to go ahead and find what acceleration is. But it's very possible here because we have a stopwatch to measure time, and we have a meter stick to measure how much distance, everything like that. That said, there's multiple ways that we can actually calculate moment of inertia, but I mean, the definition of moment of inertia is basically the sum of all your units of mass times the distance from the axis of rotation, but there's no way to actually measure it with what we have here. So we're going to go ahead and circle B and move on. So here we have a new figure. It says an axle passes through a pulley. Each end of the axle has a string that's tied to a support. A third string is looped many times around the edge of the pulley, and the free end is attached to a block of mass m sub b, which is held at rest. When the block is released, the block falls downward, obviously due to gravity, and since it's tangent to the circle on the right-hand side, we're going to have a clockwise rotation. All right, so consider clockwise to be the positive direction of rotation. Frictional effects from the axle are negligible, and the string wrapped around the disc never fully unwinds. The rotational inertia of the pulley is 1/2 mr squared, about its center of mass. Okay, great. The question is, though, how many forces are applied to the pulley axle system, and how many torques are applied to the pulley about its center when the block is released from rest? All right, so this one is actually, I think, a little confusing to some students because let's zoom in here. This pulley axle system is actually three-dimensional. There's a cable holding it up to this support on the side that is kind of closest to you and on the side that's farther away from you into the page. So there's two cables holding it up. So there's going to be a force of tension in both of those, okay? They're both going to kind of share the load, all right, in holding it and securing it to the support, to that black bar support. But regardless, if we're literally just counting the number of forces, then there's one force of tension in each of those. There's also going to be a force of tension downward from the perspective of the axle, okay? Due to tension in this cable that's holding the mast block. All right, so that's 3 forces. And then on top of all of that, there's going to be a force due to gravity downward on the wheel that's rotating. All right, so there's going to be an mg downward. So I count 4 forces acting on this rotating disc. It's really a rotating cylinder, actually. That said, there's 4 forces, but how many of them are actually generating torque? Well, if the axis of rotation is here, all of the forces acting on it are perpendicular to the radius of the cylinder, except for this one, which is tangent to its edge. So that's the only one that can actually generate torque in the first place. So we're going to look for an answer choice that says that there's 4 forces and only 1 torque. Yep, that's B. Let's go ahead and move on. Here we have a 3 kilogram horizontal disc of radius 0.2 meters, rotates about its center with an angular velocity of 50 radians per second. All right, so that first sentence is suggesting that we have some constant angular velocity, and it tells us the mass and the radius of the disc that's rotating. Then we go on to say that the edge of the horizontal disc is placed in contact with the wall, and the disc comes to rest after 10 seconds. Okay, so let's kind of imagine this really quickly. We have a spinning disc that is placed into contact with a wall, which causes it to come to rest after 10 seconds. So clearly, the contact between the disc and the wall created a frictional torque due to friction between the edge of the disc and the wall that eventually caused it caused deceleration, or acceleration in the opposite direction of the object's of angular velocity, which caused it to come to rest after 10 seconds. All right, that's great. We can do all kinds of calculations here, but it looks like the answer choices are more conceptual, so let's read them. Well, let's finish reading the question. Which of the following situations associated with linear impulse is analogous to the angular impulse that is described? Okay, so we have an angular impulse here because we know it had some initial angular momentum, and then eventually after 10 seconds it had no angular momentum. So that means angular momentum definitely changed. So that means there was impulse, because impulse is defined as change in momentum. Fine. All right, so what caused the impulse was friction with the wall, which generated frictional torque. All right, so let's see which of these linear examples from A through D represents an analogous situation, but just without any rotation. So we had a problem like this before that had us pick an analogous situation. This time we're going from rotational to linear instead of linear to rotational. So let's read A. Let's read A. It says a 3 kilogram block is initially at rest. An applied force of 3 newtons is applied to the block, but the block does not move. Right. So there is no impulse in answer choice A, because first off, the block was initially at rest, and then even after there was a force applied to it, it didn't move. So there was no change in momentum. So this problem has nothing to do with the problem that was read above. So let's look at B. It says a 3 kilogram block is initially at rest. A net force of 3 newtons is applied to the block until it has a speed of 10 meters per second. And that's great and all. But this is different from the problem that we read above, because in the problem that we read above, we have an object that has some angular momentum, and then friction, it experiences friction, and then the angular momentum goes down. For B, it had no angular momentum, and the angular momentum goes up. So right there, I don't really like that as an analogy to the problem read above. So I'm going to go ahead and say that A and B so far are kind of pretty much out for me. C says that a 3 kilogram block is initially traveling at 10 meters per second. An applied force of 3 newtons is applied to the block in the direction of its velocity for 10 seconds. Okay, so this is also an issue because, yes, we do have some angular momentum initially, but the way that it's saying that the force is applied, we know that the angular momentum is going to increase. But in our problem that we read above, the applied force causes the angular momentum to decrease. So I don't like C either. Hopefully D is much better. It says a 3 kilogram block is initially traveling at 10 meters per second. The block encounters a 3 Newton frictional force. See, I like that it's friction here because it's friction in the first place, until the block eventually stops. D is exactly right. So we have some momentum initially. Force due to friction is implemented, and then the momentum goes down to 0. D is just like the answer we read above, just in a linear form. Let's move on. All right, so we have a little bit more of a complex figure here, lots of numbers. Let's see if there's some calculations to be done. A uniform rigid rod of length 2 meters lies on a horizontal surface. One end of the rod can pivot about an axis that is perpendicular to the rod and along the plane of the page. All right, so all this is saying is that this rod is attached here to an axis of rotation, and it can pivot clockwise or counterclockwise. So a 10 Newton force is applied. All right, a 10 Newton force is applied at the midpoint with a 37-degree angle to the rod. A second force, F, capital F, is applied to the free end of the rod so that the rod remains at rest as shown in the figure. The magnitude of the torque produced by F is most nearly, so the magnitude of the torque produced by this force is what? All right, so it tells us that the rod is at rest, so that means it is in rotational equilibrium. That means there is zero net torque. So I may not know what the torque generated by this force is, but since I have the angle and the magnitude of the force here, I can calculate the torque generated by this force. And because this force would cause the rod to pivot counterclockwise, and this force would cause the rod to pivot clockwise, I know that they must be canceling each other out in order for this rod to be in equilibrium. So if I can calculate how much torque is generated here, that should be equal to the torque generated by this force. All right, so then I'm going to go ahead and write here on the left-hand side of the screen how torque is generated given the information that we have. So torque is generated as the R, which is the distance of your applied force from the axis of rotation, times the force that is perpendicular to your lever arm. In this case, the lever arm is the rod itself. All right, great. So we know how far from our axis of rotation this 10 Newton force is applied because it says it's the halfway point, and we know that the whole thing is 2. So then we know that R is equal to 1 meter. All right, so force is a little bit trickier because this 10 Newton force isn't applied perpendicular to our lever arm, and only perpendicular forces actually generate torque. So we need to find, let's zoom in here, we need to find the component of this force, this 10 Newton force, that is actually perpendicular to our lever arm. All right, so we need this force. All right, so we do know the angle that this force makes with the lever arm. So in order to find, if we see that this is a right triangle and that 10 newtons is the hypotenuse, we can find this leg pretty easily using 10 newtons times sine of 37, since that's sine gives us the leg that's opposite the angle that we know, sine 37. So that's going to be the magnitude of the force that's actually generating torque for us. So then that's what we're going to plug in for F. F is going to be equal, at least F that's perpendicular to our lever arm. And that's what this little sign here means, by the way, perpendicular. All right. F that's actually perpendicular to our lever arm is going to be 10 sine 37 degrees. All right. So now plugging that in, we have that the torque generated must be equal to 1 times 10 sine 37. And if you plug that into a calculator, make sure that you're in degrees, you'll get a torque of about 6 Newton meters. And since we know that that's going to have to be equal to the torque generated by the force that is pointing in the clockwise direction, then we know that we have the correct answer in B. Let's go ahead and move on. Here we have a light string that is attached to a massive pulley which has a known rotational inertia. Okay, so we know rotational inertia. The student must determine the relationship between the torque exerted on the pulley and the change in the pulley's angular velocity when the torque is applied for 2 seconds. In addition to a stopwatch to measure the time interval, what 2 measurements could the student make in order to determine the relationships? All right, select 2 answers. All right, so the student is trying to compare the relationship between torque and angular velocity. So the first thing I'm going to do is I'm going to give an expression or an equation that has torque and angular velocity. So I know that torque is equal to the moment of inertia, which I can use because I already know it, times angular acceleration. That's Newton's second law for rotational motion. And I can easily rewrite angular acceleration as torque is equal to moment of inertia times change in angular velocity over change in time. All right, great. So we're getting somewhere here. Now, if we're going to calculate torque separately from angular velocity, we also need to know that torque is equal to the radius of a force being applied from the axis of rotation times a force that's perpendicular to the lever arm, which in the case of a circle is just a tangent force. Okay, so if we're going to be able to calculate torque separately from angular velocity and then compare our value for torque to a changing angular velocity, then we're going to need our radius and our force here. So we're just going to pick the 2 answer choices that say that we need the radius of the pulley and the force exerted on the string of the pulley. All right. From there, we can go ahead and calculate torque using those 2 values. and then see how that torque increases. And we can also use those values to calculate our angular momentum. All right, so we can see how angular velocity. We can see how angular velocity increases as torque increases. Let's go ahead and move on. In this problem, we have a meter stick that is placed on a fulcrum here, and it is placed at its center of mass, so at its middle point. Two objects of known mass, M1 and M2, are hung at known positions on the meter stick, so we know how far they are from the axis of rotation. One end of the string is attached. Sorry, I missed a spot. So one end of a string is attached to the one end of the meter stick. Okay, so here. And the other end of the string is looped around the pulley and connected to a hanging object X of unknown mass, as shown in the figure. The meter stick does not rotate and is level with the horizontal, so we know that it is in static equilibrium, so all of the torques that are generated by all three of these masses are canceling each other out perfectly. Okay? Which of the following measuring devices, if any, should be used to make measurements to determine the unknown mass of object X? It would be nice if we could just cut it off and put it on a balance, but I don't think that's what they're asking us here. Do we need another measuring device? Well, hold on, because we know already how far away M1 and M2 are from the axis of rotation. We also know how far the force generated or the torque generated by this object is from the axis of rotation, because the actual bar is its own meter stick. All right, so we certainly don't need another ruler. Let's just say it like that, okay? Now, what I see is that we know that the sum of, like, the net torque is 0. Here, let me get my pen. We know that the net torque is equal to 0 Newton meters. And so that's going to be equal to, and we have to make a decision here, which of these masses is generating torque in the clockwise direction versus which of these masses is generating torque in the counterclockwise direction. Because this mass is clearly generating torque clockwise. This one is generating counterclockwise torque. And then this one, because it's connected to the string that would pull up, then it is generating clockwise torque. That said, let's say that clockwise is positive and counterclockwise is negative. It actually doesn't even matter, but we're just going to assign positive to clockwise and negative to counter. So then we can say that we have torque generated by M1 plus torque generated by X minus torque generated by M2. Now, breaking that up, it would be 0 is equal to, all right, it would be 0 is equal to R M1G, we know all of these, plus, all right, R MXG, all right, the only thing we don't know here is MX, and then minus R, so this is all going to be R1, R2, R3, because they're different R's, minus R M2G, and we know all of these. So we're looking at an equation here where we have one missing variable. We don't need any more instruments to figure out how much the mass of object X is. So that's pretty interesting. Let's look at the answer choices. A says a ruler because the length of the string that is looped around the pulley should be measured. All right, so that's funny because it's literally what I just said. We don't need another ruler. A protractor, nope. All of these are already applying force perpendicular to our lever arm, so we don't need any trigonometry. A motion sensor. All right, that one's actually funny. Please don't put C. D says no additional equipment or measurements are needed because the force due to gravity exerted on objects M1 and M2 and the distance between the forces applied to the tip of the fulcrum is already known. Yeah, that's exactly true. And I just showed you why we don't need anything else. We already have all the information we need to solve for the mass of object X. All right, so here we have a bar. This figure here represents the top-down view of a bar that can rotate freely about this black circle, which is the axis of rotation. So the question says a rod initially at rest, as shown in the figure, rotates freely around a pivot such that friction forces are considered to be negligible. Great. The rod is divided equally into 4 sections, with the length of each segment equal to 2 meters. A downward force of 100 newtons is applied in the position and direction shown. A student must apply a second force, we'll call it F sub 2, to the rod, so that the rod remains in equilibrium. To satisfy the condition, what magnitude of force can be exerted on the rod, and at what distance away can F2 be applied? Select two answers. All right. So this is a pretty easy question because all we need to remember is that torque generated based off of force and distance from axis of rotation is just going to be R times F perpendicular. And all of the forces here are going to be perpendicular, so we can drop any trigonometry that we might have to deal with. And R is going to represent how far away from the axis of rotation we are. All right, so F1 is pretty easy to calculate right off the bat. F1 is going to be 4 meters times 100 newtons, okay? So then we know that we have a torque, sorry, that should be a little torque 1, let's call it torque 1. We know that we have torque 1 to be equal to 400 newton meters. Great. Now we just need to see which two of these options give us 400 newton meters as well. So for option A, we have 50 newtons times 8. So 50 times 8, yeah, 50 times 8 is actually 400. So this one's going to give us 400 newton meters. So that's going to be one of them. Let me see, 150 times 6 is definitely more than 400, so we're not going to do B. 200 times 2. 200 times 2 is 400 newton meters. Because, yeah, so that's all we did here. We're just multiplying the distance times the force, and we already know all the forces are perpendicular. All right, so C is going to be one of them, and that's already 2, but let's just look at 250 times 1 meter. That's 200 newton meters, or that's 250 newton meters, so that's not what we're looking for. So A and C give us equal amounts of torque to help maintain equilibrium. Obviously, this would have to be applied upward, but yeah, let's move on. So in this problem, we have a figure of two disks that are along the same axis of rotation. Disk X is held at rest above disk Y, which rotates with angular velocity omega naught. As shown in the figure, disk Y is slowly lowered onto disk X. Disk Y is slowly lowered onto disk X. Okay, so that's a little bit of a typo, I think. I think maybe disk Y should be raised up onto disk X. All right. And remains in contact and travel together at angular velocity omega 1. Which of the following linear collisions is analogous to the rotational collision that is described? Okay, so here we go again with another analogy between a rotational motion problem and a linear motion problem. All right, so let's go ahead and read through them and see which ones kind of represent two objects that are kind of moving, or one object that's moving colliding with another object that's not moving that kind of changes their velocity, but they move together perfectly in elastic collision. All right, so block X travels towards block Y with velocity v1. Block Y is initially at rest. After the collision, block Y travels with velocity v1, and block X remains at rest. Okay, so A is not quite it, because in our situation here, they stick together and move together. In this one, they kind of separate, and the velocity is not changed. All right, so for B, it says block X travels towards block Y with velocity v1. Block Y is initially at rest. After the collision, block X and block Y travel together with a new velocity. Okay, that's basically exactly what happens here in our situation, our rotational situation above. So we're gonna put a check next to B. That sounds pretty good. I'm tempted to just circle B, but let's go ahead and see what the other situations say. Block X travels towards block Y with velocity v1. Block Y initially traveling toward blocks X with velocity negative v1. Okay, already dealing with some negative velocity is, and I'm seeing that in C and D, is definitely not going to be very close in analogy to the rotational problem that we have above. So we're going to go ahead and circle B and move on. If you have any more questions about this specific problem, go ahead and comment below. So in this problem, we have a figure and a graph. The graph has angular velocity plotted on the y-axis and time plotted on the x-axis. The question says, a group of students conduct an experiment on the rotational motion of a horizontal, rigid rod that is connected to a motor. As shown in the figure, the students collect the data necessary to create a graph of angular velocity of the disk as a function of time. One student in the group states that the graph shows that a net external torque is exerted on the rod because the rod's angular momentum increased. Do the data support the student's statement? All right, so, before I even look at the answer choices, I'm just going to investigate the graph here, because if angular velocity is increasing with respect to time, this brings to mind, to me, the mathematical definition for angular acceleration, because it is change in angular momentum. Sorry, not angular momentum, angular velocity over change in time. All right. So that means that angular acceleration is the slope of this graph because it's change in velocity over change in time. All right. Change in y over change in x, that's slope. All right. So we have some acceleration. So that means acceleration is not 0. All right. That said, according to Newton's second law, torque is I moment of inertia times angular acceleration. So if angular acceleration is not 0, all right, if angular acceleration is not 0 and moment of inertia is never 0, then that means that torque must be non-zero as well. So that's my argument as to why I know that there's a net torque acting on the rod. Let's see what the answer choices are. So first off, C and D both say no. There's no net torque. The student is wrong saying that there's a net torque, so I'm going to cross those out immediately. A and B, let's read what we have. It says, yes, because the angular velocity increases with time, therefore the angular momentum of the rod increases with time. This can only occur as a result of net torque. Yeah, I mean, that's exactly true. And that kind of is what we're arguing here. We're saying that if velocity is increasing with time, then acceleration, we have some positive acceleration, and therefore we must have some positive torque. Great. B says yes, because the area bound between the best fit line and the horizontal axis is a positive value. Therefore, angular displacement of the rod is non-zero. This can only occur as a result of net torque. So, all right, so that first part of B is correct. Actually, the first two sentences of B is correct. The angular displacement is non-zero, and it is due to the area underneath the curve. All right, but it's not true to say that this can only occur as a result of net torque. If the rod already had some angular velocity that was constant, then it could be in equilibrium with no net torque, and the displacement could still be increasing. So we could have a straight line here, which suggests no acceleration and no net torque, and still have a positive value underneath that straight line between the graph and the horizontal axis. So B does make an incorrect statement in its last sentence, so we're going to have to go ahead and circle A here and move on. So here we have a figure of two students on a seesaw. All right, and the fulcrum is assumed to be at the center of the actual bar that makes up the seesaw. The two students, X and Y, sit on a seesaw that is in static equilibrium, as shown in the figure. The fulcrum is located at the center of the seesaw. The mass of student Y is known, okay? A third student Z must determine the mass of student X. Which of the following measurements should student Z make in order to determine the mass of student X? Well, if we know how to find torque based off of mass, then, or at least force due to gravity in this case, then we know that we could have torque if we knew how far we are from the axis of rotation times the force that's perpendicular to the lever arm. In this case, the lever arm is the seesaw, and that force is going to be made up of force due to gravity. So I'm just going to go ahead and say mg, where m is the mass of the object that is, generating the torque. All right, so we know that for student Y, we know the mass, but we don't know how far they are from the axis of rotation. So we know mass, we know gravity, but we don't know r. Now, if we wanted to then compare the torque generated by student Y with the torque generated by student X, we know that those torques have to be the same because the seesaw is in static equilibrium right now. So that means that r of x, distance that student X is from the axis of rotation, times the mass of student X times the acceleration due to gravity must be equal then to r sub y, m sub y, times g. So we know I'm going to highlight in pink what we know. We know g, we know the mass of student Y, and we know g over here. If we needed to find m, the mass of student X, what we need to be able to measure the distance that student X is from the axis of rotation and the distance that student Y is from the axis of rotation. Then we'd have just one missing variable and we could solve for the mass of student X. All right, so let's see what the answer choices are. The length of the seesaw, because the entire length of the seesaw is in static equilibrium. Okay, if we knew the entire length of the seesaw, that'd be great, but that doesn't necessarily mean that we know how far each student is from the axis of rotation. So that's not, just that by itself doesn't help us enough. B says the distance the student X is from the edge of the seesaw and the distance that student Y is from the edge of the seesaw, because the seesaw would no longer be in static equilibrium. Now, oddly enough, A and B together would help us, but either of them by themselves don't tell us how far each student is from the axis of rotation. So C then says the distance that student X is from the center and the distance that student Y is from the center, because these are the distances from the fulcrum to the location of the forces exerted on the two-student seesaw system. Yeah, that's exactly what we're talking about here, the distance each student is from the axis of rotation. So I'm going to circle C. D just says the mass of the seesaw. That's not going to help us at all. All right, the mass of the seesaw is not actually generating any torque. So C, and let's move on. All right, so here we have a disk rotating about some center axis of rotation and a graph of the torque, the net torque on the disk with respect to time. So anytime you see a torque versus time graph, then you're probably going to be dealing with impulse or change in momentum in some way, because that's really the only thing we really use the torque versus time graph to show impulse. So a solid disk rests on a central axle. A string is wound around the disk, which causes the disk to rotate about its axle when pulled with the constant force F sub p. The force is exerted on the string until the string completely unwinds and detaches from the disk after 2 seconds. The graph of the net torque as a function of time is shown. How can a student determine what the change in angular momentum of the disk would be? It would be between 0 and 2 seconds. If friction were negligible, justify your answer. Okay, that's a typo. Friction is not negligible here. Okay, friction is not negligible here because we can see in the graph very clearly that after the 2 second mark, we have negative torque. That negative torque, based off of the free body diagram here, because there's no other applied forces, must be due to frictional torque. All right, so we're just going to pretend like that friction is negligible part is not there. All right, so based off of what we see on the graph, we can see that in the first 2 seconds, the net torque is 3 Newton meters. And so that means that the torque generated by F sub P must be 4 Newton meters to counteract the -1 Newton meter frictional torque that we know is there the whole time. All right, because we know it's there because as soon as we stop applying that force, that's exactly what the torque goes to. All right, -1. So the net torque is at 3, but the torque generated by the applied force must be 4. 1 Newton meter of that is canceled out by the friction. Okay, so that's about everything here. Let's see what the answer choices are. Oh, but also before we read the answer choices, just a reminder, area underneath the torque versus time graph is impulse or change of momentum. So like, let's zoom in here. The area, if we're just looking between 0 and 2, the area between the graph and the horizontal axis is our change in momentum. So that'll also be true after we let go. Our change in momentum is going to be the area in between our graph and the horizontal axis. So that's what impulse is. Oops. All right. Now let's read our answer choices, because it's saying how can the student determine the change in angular momentum? The answer should just be find the area underneath the curve, but whatever. The net torque, answer choice A says the net torque exerted on the disk during the time interval 0 to 2 is 6 Newton meters. All right, so we know that that's not true. We've already know that it's the net torque is 3 Newton meters, so that's out the window. Also, that's the same opening sentence that D has, by the way. So we're going to just chop out D. So between B and C, the net torque exerted on the disk during the time interval is during the first 2 seconds is 3 Newton meters. That's true. After that, the net torque, which is the frictional torque, is -1. Okay, that's true. Using this information, it can be inferred that the torque due to friction, the torque due to the applied force is 2 Newton meters. No, we can see that it must be 4 Newton meters to counteract one of the -1 Newton meter of frictional torque. So B isn't correct. That leaves C, and you can see the correct answer here. The 4 Newton meters is the applied torque. Therefore, the change in angular momentum from the applied torque, if friction were negligible, would be 4 Newton meters multiplied by 2 seconds. That would give you the area underneath this curve, and that's correct. It's just, I think it's interesting that the answer choices here didn't really evolve around how to find momentum. There was more like, can you decide how much torque there actually was? It's a weird problem. And it's actually misleading suggesting that friction was negligible, because if friction was truly negligible during the first 2 seconds, then we would have had a net torque of 4 Newton meters. But that's not what the graph suggested, and neither did any of the answer choices truly suggest that. So let's go ahead and move on. So this question again has a figure and a graph. The graph is angular momentum with respect to time. And before we even get into the question, because sometimes, it's just good that when you see an angular momentum versus time graph, you have to think, okay, what's the slope of this graph gonna mean? Because change in momentum over change in time, what is that? That's gonna be torque. Okay, cool. So just keep that in mind for the question. That's at least the first thing I think of when I see a graph. I'm like, all right, what do the components of this graph actually represent for me, physics principle wise? All right, so it says a vertically oriented rod may freely rotate around a horizontal axis through its center. Okay, so I guess this is the axis. A student applies a force on one end of the rod so that the rod rotates around the axis. The student collects the necessary data to generate the graph that is shown. After observing the data, the student makes the following statement. For the time interval shown, the magnitude, it's an important word there for this problem, of the net torque exerted on the rod decreases over time. Okay, so the net torque is the slope of this graph. We discussed that when we started. And the slope is constant. It's a straight line. So the magnitude of this slope is the same from 0 to 10 seconds. So first off, no, the magnitude of the rod does not change at all over time, or at least not over these 10 seconds. So the student statement is wrong. Do the data support the student statement? No. So it's not going to be A or B, but let's see what C and D say. C says no because the angular momentum decreases to 0. Okay. Just because it decreases to 0, I don't think is proof that there's no torque, because there could have been torque. There could have been, or at least just because it decreases to 0 isn't proof that the net torque decreases over time. The torque could have been decreasing as it was getting closer to 0. So then D says no because the slope of the best fit line remains constant. Yes, that's exactly why we know for sure that there is no change in the torque, because the slope of the best fit line is constant, suggesting that the torque stayed the same. So in this problem, we have a graph that is torque plotted against time. And like I've probably already said, anytime we have a torque versus time or force versus time, we know we're dealing with impulse. In other words, change in momentum. So in this experiment, a student applies a net force to the edge of a disk for 10 seconds. The student may change the magnitude and the direction of the force at any time in the experiment. A graph of the net torque exerted on the edge of the disk as a function of time is shown. After observing the graph, the student concludes that the angular momentum of the disk has not changed. Does the graph support the student's conclusion? Absolutely not, it doesn't, because what you remember is that the area underneath the curve, or the area underneath the function, on a torque versus time graph represents angular momentum. And the area underneath this curve is not 0, because this is the area of a triangle. All right. So yes, the torque ends off at 0 and started off as 0, but there was definitely a change in angular momentum along the way because of the fact that there is a non-zero area underneath this function, or between this function and the horizontal axis. So the answer is no. So let's go ahead and drop A and B. Now let's look at C and D. It says no because the area bound by the curve. Yep, that's it. That's what it is. All right. Let's move on. All right. So in this figure, we have a disk that's rotating with, it seems like, an axis of rotation at the center, so that our r, or distance from the axis of rotation, for a tangent force is going to be ½ meter. So in the experiment, student must determine the angular momentum of a vertically rotating non-uniform disk of diameter 1 meter. A central axis of negligible friction is located at the center of the disk and is oriented perpendicular to the plane of the page. Fine, so it's like at the center of this disk. A string is wound around the disk, and an object is of unknown mass is attached to the string, as shown in figure 1. The object is released from rest, which causes the disk to rotate as the object falls. The disk's angular position as a function of time is shown in figure 2. Well, figure 2. There's no figure 2. All right, whatever. That's fine. Let's see if we can answer it anyways. The tension in the string is 5 newtons and remains constant. Okay. Which of the following mathematical routines could a student use to determine the change in angular momentum of the disk during a time interval delta t? Justify your selection. Okay, so let me read that one more time. Which of the following mathematical routines could a student use to determine the change in angular momentum of the disk? All right, so change in angular momentum is impulse. Impulse-force relation is delta L is equal to, or I should say impulse torque relation, because we're talking about rotational motion, T delta, torque delta T, all right? And if we wanted to figure out what the impulse was, then we would need to know what torque is, and torque is defined as, and since the tension in this cable is tangent to the circle, we already know it's perpendicular, so we don't need, we know it makes a 90-degree angle. We don't need the trig functions because sine of 90 is 1. That said, we can say that the impulse or change in momentum is equal to RF delta T. Yeah, RF delta T. So this is what we would need in order to go ahead and find that change in angular momentum. Let's see what the answer choices say. All right, it says, so all of them say to use the torque impulse relation. And then A says torque is equal to RF sine theta, where theta is equal to 0 degrees. And that's not true. Theta would be equal to 90 degrees in this case, because the angle that our tension here makes with the radius of the circle is 90 degrees. So either any of these that say theta is 0 is out. So between B and D, we have RF sine theta for our torque, RF sine theta. Oh, and then so the difference here is that for B it says the radius is a half a meter, and for this one it says the radius is a whole meter. The radius is half a meter because the diameter of the circle is a whole meter. So the distance from our axis of rotation is half a meter. B is the correct answer here. So in this problem, we just have a graph, and it's velocity versus time. All right, and it looks like we have some constant acceleration because the slope of a velocity versus time graph is acceleration. So that means we have some constant force being applied that's causing this velocity to increase. And that's just my initial analysis of the graph before I even read the question. Let's read the question. In an experiment, a disk of known rotational inertia I rotates as a result of a known force that is applied to the disk's edge. The angular velocity of the disk is measured as a function of time, as shown in the graph. Great. Students must determine the relationship between the magnitude of the change in angular momentum of the disk and the torque applied to the disk. Okay, so we're trying to figure out the relationship between increasing velocity and torque. That's great. So what quantity could the students measure in order to make the determination? So what do the students need in order to figure out a relationship between increasing velocity and, well, what's going to be increasing torque? Well, not necessarily increasing torque over the course of the 10 seconds, but let's see. Okay. We know that torque is defined as moment of inertia times angular acceleration. And because we're dealing with a velocity versus time graph, we can find that angular acceleration as the slope of our change, or basically the change in velocity over change in time. So we can say that torque is equal to moment of inertia times change in angular velocity over change in time. And that's great because we know what our moment of inertia is, we know what our time period is, and we know what our change in velocity is. And so we can figure out what our torque is there. But in order to compare the increasing omega with torque, then we'll have to calculate torque in some way that has no respect to angular velocity. And we have an expression for that. That's going to be RF. The thing is that we know what F is, and it made a statement to tell us that we know what F is. So in order to calculate a changing torque without velocity, then we'll have to have the radius of the radius or the distance from the axis of rotation that our torque is being applied. So if it's a disk, then it's the radius of that disk. So if we can measure the radius of the disk, we would know everything we need to calculate torque, both with respect to angular velocity and without a respect to angular velocity. That means that, looking at the answer choices, if we can measure the radius of the disk, we'll know everything we need. All right, so here we have a graph that kind of looks a little bit scattered, but there's clearly a line of best fit that is linear here. It's certainly not any kind of exponential relationship, and it's not really all that scattered to suggest that it's some kind of scatter plot. Anyways, the question says, in an experiment, an external torque is applied to the edge of a disk. Okay, let me actually pause right there because we're talking about rotational motion because we have external torque being applied to the edge of a disk. But this graph is actually tangential speed with respect to time. So don't let that confuse you. This is not angular velocity. This is tangential speed. So we're probably going to have to do that relationship between velocity between a rotational quantity and a linear quantity. Let's just continue reading the question. In an experiment, an external torque is applied to the edge of a disk of radius 0.5 meters, such that the edge of the disk speeds up as it continues to rotate. The tangential speed as a function of time is shown for the edge of the disk. The rotational inertia of the disk is 0.125 kilogram meters squared. Can a student use the graph and known information to calculate the net torque exerted on the edge of the disk? Great. Okay, so yes, first off, but let me show you why. We know that torque is equal to moment of inertia times angular acceleration. Now, we may not know what the angular acceleration is based off of this graph, or at least not immediately, but we do know that this graph, at least the slope of this graph, or at least the slope of the best fit line to this plot, does give us linear tangential acceleration. And we know that if we take our linear tangential acceleration and divide it by the radius of our disk, then that will give us angular acceleration, because that's how linear and angular components are typically related, just as a factor of the radius. So if we take our linear acceleration divided by the radius of our spinning disk, then that gives us the angular acceleration that we're dealing with. So we know the radius of the disk. We know that it's 0.5 meters. It made sure to give us that. We also know the moment of inertia. So that said, if we can take the slope of this graph to find A, then we can go ahead and divide it by R and multiply it by I to get torque. So yes, that's what we need in order to get torque. And yes, we can find torque. Its I is equal to, T is tau, torque is equal to I times A over R. All right, so yes, we can find torque. So I'm going to cross out C and D because that says no, we cannot find torque. But let's see what the difference between A and B is. Because the slope of the graph multiplied by the rotational inertia is equal to the net torque. All right, that's not true because the slope of the graph is linear acceleration. We would need it to be angular acceleration if we wanted to just go ahead and multiply it by a moment of inertia. So A is not correct. That means B is the correct answer, but let's go ahead and read it to double check why. Because the change in tangential speed per unit of time can be multiplied by the rotational inertia and then divided by radius. Okay, so that's exactly what we have going on here. We're going to multiply that slope by a moment of inertia and divide by radius to get the torque. All right, guys, let's move on. So in an experiment, one end of a string is attached to object X, which we see here, and the other end is attached to object Y, which we see here. The string is then placed around a pulley as shown in the figure. And the system containing object X, object Y, the string, and the pulley remains at rest. So it's in static equilibrium. So before we even finish reading, let me just say, that means that the torque generated by object Y is equal to the torque generated by object X. So a support string connects the pulley to the ceiling. Okay, cool, I see that. Which two of the following measuring devices could students use to mathematically verify that the net torque exerted on the system is 0? Select two answers. Okay, well, in order to mathematically verify anything about the torque, we need to know the relationship between, like, how to find torque. So the physics principle between how to find torque. We know that we need to know the radius of the pulley system, and we need to know the force being applied. Okay, so the force being applied is literally just gravity on objects X and Y. All right, and that gravity is perfectly tangential. It's being applied perfectly tangential, so we don't need anything with angles. We're dealing with right angles here. All right, so then that torque is going to be equal to the radius of our pulley system times the force being applied, which in this case is mass times gravity. We know gravity. We always know what gravity is, or we can at least assume that we know what gravity is. But what we don't know right now is how big the radius of the pulley system is, or the mass of the object. So we're going to need something to measure the mass of the object and also to measure the radius of the pulley system. So to me, that's a meter stick and an electronic balance. Let's move on. In this problem, we have a figure in which it looks like a disk, and based off of this arrow is probably moving onto a disk above, which is moving with angular counterclockwise rotation, and then a disk below that's moving with angular clockwise rotation. So they're moving in opposite directions. They're about to actually collide. So let's see what the question says. Two identical disks rotate about their centers in opposite directions with the same magnitude of angular speed. Okay. They're identical disks. That means they have the same moment of inertia and they currently have the same angular velocity. Okay, that's interesting. Just in opposite directions. So the top disk is dropped onto the bottom disk as shown in the figure so that they collide and stick together. Which of the following predictions is correct? Well, if I know about their momentum, right? So this is going to be almost like a conservation of momentum problem. If they're identical disks and momentum is defined as L is equal to I omega, and these two numbers are the same for both of them, when they collide and if they stick together, yeah, because it says then they stick together, then that means their momentums are going to literally cancel each other out so that both of their velocities should go to zero. So let's see what the answer choices say. A says each disk will spin with the same final angular velocity, which is zero. Well, that is what I just said, so that sounds pretty good right there. Let's see what the other answer choices say. First off, one thing we know is that if they stick together, their final velocities will be the same. Okay, so, and that's what they all say, so that's good. All right, so each disk will spin with the same final angular velocity where their final velocity is greater than their initial velocity. Well, their initial velocity was non-zero, so their final velocity is certainly not greater than that if their final velocity is zero. All of these other choices suggest that their final velocity is bigger than zero, and we pretty much can prove pretty quickly that it's not, that their momentums are going to cancel each other out, so their velocities are going to go to zero. So we're gonna circle A here and move on. All right, so we have a table here, and the question says students place the center of mass of a meter stick at the tip of a fulcrum so that the meter stick does not rotate. All right. 3 objects of various mass are placed at different positions on the meter stick, as shown in the table. A 4th object is placed on the meter stick so that the meter stick and all 4 objects remain in static equilibrium. Which of the following could represent the mass of the object and its position on the meter stick? Okay, so it's saying that there's 4 objects that are attached to the meter stick, all have their own mass and their own position on the meter stick. And I see a typo because I'm pretty sure this should be centimeters, because I don't think that any of these objects are 20, 60, or 70 meters away from the center of a single meter stick. So to make this simple, instead of changing that to centimeters, I'm actually going to add a decimal before all of these, which represent centimeters anyway. So 0.2, 0.6, 0.7 meters away from 0.7 meters away. Yeah, okay, so position on the meter stick. Great. So we know that, we might have to actually draw this a little bit. Let's draw kind of a bar that's going to represent the meter stick, and then a fulcrum that's going to represent where the meter stick is attached. So let's go ahead and say that this meter stick is attached to the fulcrum at its center point. All right. The center point is going to represent 50 centimeters or 0.5 meters. So anything greater, as far as the position on the meter stick over here, if you look back at the table with me, anything greater than 50 is going to be on the right side of the meter stick, and anything less than 50 is going to be on the left side of the meter stick. And that really matters because objects hanging from the meter stick on the right side are going to be generating a torque that is clockwise, and objects that are on the left side of the meter stick are going to be generating a torque that's counterclockwise, because they'd make the ruler rotate in a counterclockwise direction. So that's important to visualize properly there. So first, we're going to just have to figure out how much torque is generated, because if we know that the object is in static equilibrium, then the sum of all the torques must be equal to 0. So if torque is equal to distance from axis of rotation times force that's perpendicular to the axis, well, we can assume that the force due to gravity in all these objects is going to be perpendicular to the lever arm. The lever arm being the ruler, so we can throw out any trigonometry here. And we can just say that torque 1 due to object 1 should be R, which in this case R is going to be 0.3, and I'm going to tell you why. The 0.2 mark on the meter stick over here somewhere is going to be 30 centimeters from the 50 centimeter mark. 20 plus 30 equals 50. So I'm going to assume that we're 30 centimeters or 0.3 meters away from that axis of rotation. All right, and we're going to go ahead and multiply that by the force due to gravity on that object. And because its mass is 0.5, I know that 0.5 times 10 meters per second squared, which is what we're going to assume that the acceleration due to gravity is, will just give us 5 newtons. So we have 5 here. All right, great. So I'll calculate that in a second, but we have torque 2, which is going to be basically the same kind of concept. We're going to be 10 centimeters from the axis of rotation. So we're going to have 0.1 times and then 3 newtons, all right, because the mass is 3. So torque 3 is going to be equal to, looks like 0.2 meters from the axis of rotation times 2 newtons, because it's 0.2 kilograms times 10 meters per second squared. All right, and then T4 is going to be unknown. T4 is going to be unknown. So these are all going to be equal to their own torques. All right, and now we're going to have to assign a positive value to one of the directions and a negative value to the other direction. So I'm going to go ahead and assign a positive value to the clockwise direction and a negative value to the counterclockwise direction. I have to do this so that things add up together properly and go to 0 when they should. All right, so I'm going to say that objects on the right-hand side are going to cause a positive rotation and objects on the left-hand side are going to cause a negative rotation. So object 1, being at 0.2, is going to cause a negative torque. Now, that's object 1. Object 2 being on the right side is going to cause a positive torque. Object 3 being on the right side is going to cause a positive torque. And so let's go ahead and calculate these really quickly. So 0.3 times 5. Let me grab my calculator. 0.3 times 5 gives us 1.5. All right. And then 0.1 times 3, that should just be 0.3. And then 0.2 times 2, that should be 0.4. Great. Now, these two together make 0.7. And if I take 0.7 and combine it with negative 1.5, I just get negative still 0.8. All right. So that means I need the torque of 4 to still be positive 0.8 in order to actually set this all to equilibrium so that this all together can cancel itself out. Great. So then which one of these answer choices actually give me a torque of 0.8? Well, let's figure it out. If the mass were 12, all right, so then, and the position on the stick were 16, then we're going to need it, that will give us a torque of, and remember, it needs to be positive torque, so that means it has to be on the right side, so we can cancel out C and D because position 34 centimeters are both on the left side. But the torque here would be 0.16, because it's 16 centimeters from the axis of rotation, times 1.2. All right, and then the torque of option B would be, the torque of option B, so the torque of option B would be 0.16 again, times 5. All right, so looking at this, it's looking like B, but we'll go ahead and calculate it anyways. 0.16 times 1.2 equals less than 2. So actually, less than 0.2 is what I meant to say. So this is equal to 0.192. That's not enough, so it's probably going to be B. Let's go ahead and calculate it. 0.16 times 5 is equal to 0.8. 0.8. And that's exactly what we needed to be, positive 0.18. The answer is B.